Hey everyone, in this video we're going to be looking at categorical predictors and dummy variables in relation to predictive modeling. So we're going to talk about what a dummy variable is, why it's useful, and how it can help us in predictive modeling. And we'll talk about how we can interpret the effects, the estimated coefficients for categorical predictors when using linear regression and predictive modeling more generally. The data set we're going to be using in this activity to demonstrate these concepts is the Palmer Penguins data set again. So as a reminder, this is a data set on a few hundred penguins. It's an actual real-life data set collected on these penguins in Antarctica. At this research station, there was 3 different species of penguins, and the penguins were found across 3 different islands. We have data on the penguins. There's many variables. The ones we're going to be focusing on in this activity, and here's just a subset of the data, for example. The species of the penguin is a categorical variable, and the sex of the penguin, being male or female, is another categorical variable. So we're going to look at how we can model the body mass of the penguins in this activity as our quantitative response variable, but now also using categorical variables as predictors. We're going to see how we can do that in predictive modeling. So to start, before we get to categorical predictors, let's have a very quick review of how we can interpret the effects of a quantitative explanatory variable or a quantitative predictor variable. So as a reminder, for example, we can model the body masses of the penguins using their measured flipper lengths. Okay. So one quantitative explanatory variable, flipper length, and one quantitative response variable, body mass. Visualizing the distribution of the two, we get this scatter plot, and we have our straight line of best fit corresponding to a simple linear regression model. Okay. And this line of best fit is defined uniquely by a y-intercept, an estimated intercept term, and a slope, which determines how steeply the line increases or decreases. Okay. So here, for example, is our estimated linear regression model, where we're modeling a penguin's body mass. So y hat is the estimated or predicted body mass of the penguin, and x1 is a penguin's flipper length in millimeters. Okay. So again, just as a review real quick before we get to categorical variables, let's see how we can interpret these estimated terms for this simple linear regression model, okay, when we have a quantitative predictor. So for the slope, we'd say since the estimated, I'm sorry, for the intercept, let's start with the intercept here. So since the estimated intercept is this value, well, it's negative, which is not sensible for a body mass of a penguin. But the bigger issue here is that the intercept is the expected value of the response given that x is 0. In this case, since a flipper length of 0 millimeters is outside the scope of this observed data set, and also not practically possible, interpreting the intercept here would be extrapolation, and thus it's inappropriate in this setting. And so since we can see here from the scatter plot, 0 is well outside the range of the observed x values, we don't interpret the intercept term. It's inappropriate to do so. That's a separate fact from it being negative. That's also problematic. Since we know it's impossible for a penguin to have a negative body mass, we would never want to interpret this value anyways, even if it wasn't extrapolation. But extrapolation makes it inappropriate. Okay, but for the slope, here's what we can say for the slope. So since the estimated slope for flipper length is 50.2, you can say that for every 1 millimeter increase in a penguin's flipper length, we expect their body mass. And this part where we say we expect is really important because it's saying it's our best guess, but it's not a definitive relationship here. So it's really important that we add the phrasing we expect, or on average, their body mass will increase by 50.2 grams. Okay, so that's how we can interpret the estimated slope here. We talked about how the intercept was inappropriate to interpret in this setting because it would be extrapolation. Since the x value is outside the 0 is outside the range of the observed x values. All right. But let's see, what if we wanted to incorporate categorical variables in our model? Okay. In this case, let's look at, for example, we still have this plot of body mass by flipper length. Okay, that's pretty good linear relationship here. What if we colored the points based on whether the penguin was recorded as being male or female? Now we see here's our distribution of points. And we can see, for example, that the green points seem to be a little bit higher typically than the blue points. So males typically have higher body masses on average, it looks like, than females. So that seems like important information that if we're making a predicted value, it would be good to account for that. If we know whether the penguin is male or female, we can get a more accurate predicted body mass if we incorporate this information into our model as well. So how can we do that? Since this is categorical information, but linear regression is based on numerical optimization. It involves derivatives, calculus, everything that's based on solely numbers. Okay, so how can we incorporate whether each penguin is male or female into the modeling process? Well, we'll talk about that. First, so the scatter plot is one way to show or explore that, okay, maybe males look like they're a little bit higher on average. An easier way to compare a response variable, in this case body mass, across the levels or groups of a categorical variable is to use side-by-side box plots. That's sort of the go-to plot because it makes it much more clear than the scatter plot here that males, for example, have larger body masses typically than females. So here we can see, for example, the median male penguin body mass in this data set looks like it's about 4,200, 4,300. And the median female one is about 3,800 maybe. So does the penguin body mass appear to vary based on whether it's male or female? So yes. male penguins have larger body masses. And then it's important to add on average, because there are individual female penguins that have larger body masses than some male penguins. So this is just on average. So it's important to include that phrasing in there. Okay, so back to the original point of how can we incorporate this categorical information into a predictive model? Since we know it's important, we know it would make our predictions more accurate. Well, in general, for all predictive models, not just linear regression, which we're focusing on here, but if you go on to learn more advanced predictive models, it's often the case that categorical information is important to consider. And this is allowed in general. Predictors can be quantitative or categorical. But since solutions for the model estimates are based on numerical optimization, they're based on numerical algorithms, we have to use some clever tricks to encode the categorical information in a quantitative way. So the most common way this is done is to use what are called dummy variables. So a dummy variable, also called an indicator variable, is a binary variable, so it takes on values of either 0 or 1. This is the most common way this is done, to indicate the presence of an effect or outcome. So in other words, to indicate the category that that observation belongs to. So for each categorical predictor, the number of needed dummy variables is LK minus 1, where LK is the number of levels of the kth predictor. If you go on into machine learning or data science, you may hear this process of encoding categorical variables as binary variables. Some people refer to this as one-hot encoding, which I think sounds a little bit fancy. It's essentially representing categorical information as numerical values. So this is a necessary step. If you want to use categorical predictors in a model, you have to encode them as dummy variables prior to fitting a model. However, most software does this automatically now. So you won't really see the process of this explicitly underneath, but we'll look at it more explicitly here in this activity. So when creating dummy variables to represent or encode categorical information, it's typically the case that one subgroup or one subcategory is set as the baseline or reference category, which means that that category does not get its own dummy variable, but all other subgroups each get their own indicator or dummy variables. Okay. So for example, if we want to incorporate the sex of the penguin in a model, this has L equals 2 categories. So we only need one indicator variable to represent the sex of the penguin. For example, it could be an indicator variable saying whether or not the penguin is female. The reason we only need one indicator variable is because if we know that the penguin's female, then we know it's not male, since there was only 2 categories in this data set. And if we know that the penguin's not male, we know that it's female. So we only need to know the indicator variable for one of the groups, and the other one's redundant. So we only need one dummy variable to represent this variable. So let's look at a couple quick examples. Let's say we want to predict how many points a basketball team scores using whether they are playing on their home court So their own home stadium, away at a different team, or on a neutral court that's neither their home arena nor their opponent's arena. That's an important consideration. It's known that teams do better, score more points typically when they're playing at home in front of their home crowd versus away. Okay. So there's 3 different categories here. That would be an important predictor, categorical predictor to include in a model for predicting how many points a basketball team scores. Another example, maybe we're estimating we have a clinical trial, we have a new drug we're trying to develop to lower people's blood pressures. So we have our new drug we're proposing, drug A maybe, and then there's a current drug, drug B, and then we also have a placebo, a drug that has no active effect. Okay, and we want to see if our new drug does better than the current drug or if it does better than a placebo. We're curious about that. So how many dummy variables would be needed to incorporate the categorical information in each of these? So for example 1, since the location home, away, or neutral has 3 possible categories, we would need 2 dummy variables to incorporate location as a predictor in a model for as a predictor when modeling how many points a basketball team scores. Okay. And in example 2, since the treatment, which was drug A, drug B, and placebo, since the treatment had 3 possible categories, we would also need 2 dummy variables to incorporate treatment as a predictor when modeling patient blood pressures. Okay. And then we can go a little bit further to say, in this scenario, making neutral the baseline or reference category, likely best since, or is likely preferred, I would say, since this would allow us to directly measure the effect of a team playing at home or playing away. And in example 2, in this scenario, making placebo the baseline or reference category is likely preferred, since this would allow us to measure the effect of drug A and drug B compared to a non-active drug. Non-active drug. So those are some examples where categorical information would be important to include, and we could do so in a predictive model using dummy variables. Okay. So let's look at what does a dummy variable look like. Okay. So considering the same exact data, the Palmer penguins data, okay, we had these randomly selected rows. This is not the whole data set. These are just 5 randomly selected rows. Okay. And when the data is stored in like a CSV file, this is how it looks. Okay. Body mass and flipper length have numbers. These columns can be directly used in numerical algorithms, right? They're good to go. Species and sex take a little bit of extra work though if we want to use those as predictors. So how can we do that? Well, what we can do, for example, to use sex as a predictor in a model for predicting the body mass of a penguin is, since sex had 2 levels, male or female, in this data set, we need 2 minus 1 equals 1 dummy variable to encode that information. So the dummy variable here, which is called sex female, is an indicator, a binary indicator variable of whether or not the penguin is female. So it's 1 when the penguin's female and 0 otherwise. Again, note that we do not need another indicator for male. We don't need sex male, because it would be 1 if the penguin's male, 0 if it's female, and so on. But that tells us exactly the same information as this column, so it would be redundant. We don't need to include that as an extra predictor, because this column already tells us whether or not the penguin is male or not, since there's only 2 possible categories. And you may be wondering, well, what if we had more than 2 categories? Well, if you have more than 2 categories, then you have more than 1 dummy variable. Okay, but you always have 1 less dummy variable than the number of categories to avoid redundancy in the predictor variables. Okay. So let's look at visually how the sex of the penguin is informative of the body masses here. Okay. So each point here is representing the measurement for a penguin of its body mass. And then we have the female indicator variable. So 0, here's all the male penguin measurements. And here's all the female penguin measurements. So we can fit a simple linear regression model. Now that we have all numbers, we can use sex female as a predictor in this model to predict body mass. So essentially what we've done is we've turned the categorical information into just a quantitative variable. That's our dummy variable. And now we can use simple linear regression just as we did before. So we have 1 predictor, which is the dummy variable. So this is x1 is 1 if the penguin's female, 0 if it's male. And here's how the difference in the body masses between male and females look. Okay, so we drew a line here. The green line is the average body mass for all the male penguins. The blue line is the average body mass for all the female penguins. And what you'll notice now in the model output, the estimated model output, we have this. So we can interpret these estimates by seeing that the average, in this case, because we just have 1 categorical predictor with 2 columns, with 2 categories, the intercept gives the average body mass of the male penguins, exactly what this number is. And the estimated slope for the dummy variable for female is the difference in heights between the average, or the difference in the average body mass for males and the average body mass for females. This distance is 683.4. And because the males are higher, it's a negative effect for the females. So these have very interpretable meanings that can be visualized here in this type of. So here's our estimated model, where now we define it as we say, so y hat is the same as usual. It's the estimated or predicted penguin body mass. X1 we describe as, since it's a predictor variable, we always say it's 1 if this, in this case, if the penguin's female, and 0 otherwise. In this case, 0 if the penguin's male. So in this case, which group was designated as the referenced or baseline category? So since X1 is 1 if the penguin's female, male penguins are the baseline or reference category we call it. Since X1 is 0 for males, males are the baseline category. How do we interpret the estimated slope? Okay. The slope, the estimated slope is negative 683.4, which tells us that female penguins have an average body mass so that's how we can interpret the slope here. Female penguins had an average body mass that was 683.4 grams less than that of male penguins. So notice we don't say the negative in our interpretation, we just say less than. And then for the intercept, like we said, the estimated intercept is 35.7, which tells us that the average body mass of male penguins was that many grams. Okay. So how can we get the expected or average, estimated average body mass of female penguins? In other words, a predicted body mass for a female penguin. So we can use our estimated regression equation. And just like always, so this is a predicted value. So we just think about like this, and then, okay, so we plug in for X1. What is X1 when the penguin's female? It's 1 if the penguin's female. We plug in 1 here, see what this equals. And we can use Google to calculate that value. And that many grams. Okay. Good to include the units of measurement. It's important. We need to include the units of measurement in this predicted value. Okay. So 3,862 grams. Let's look at the scatter plot or the plot above and see if that seemed reasonable, right? Always good to double check. So we knew here was the average for the female penguins. Okay, that seems reasonable. It looks like it's about 3,700, right? Or let's see. So yeah, that seems reasonable, right? 3,900, right? Almost 3,900. Yeah, that's right where the blue line's at. Okay, so that's actually right here is the predicted value for the body mass of a female penguin, right at this height. Okay. So you can always double check your predicted values if you're given visualizations like that. So we would use the predict function in R if we wanted to get predicted values. We wouldn't really use the output and manually calculate it ourselves. But it's good to know how to write out the estimated model. It's important to be able to do that and to understand how predicted values are obtained by R. So the R code below, appended at the bottom of the document, shows how we could use R to calculate this predicted value, but we're just doing it by hand here for practice. All right. So that was how we could use just a categorical predictor in a model with nothing else. Okay, but we've looked at multiple linear regression, and we know that we can use multiple predictors in a model. Okay, so we can incorporate flipper length as a predictor simultaneously with the sex of the penguin and get an even more accurate prediction now. Okay. So in this case, we have x1 is the indicator of a penguin being female or not, and x2 is the penguin's flipper length. And now we have a two predictor model where we have categorical and quantitative predictors now. Okay, so we get these estimates, and that implies this estimated regression equation. Okay, so here's how we can get a statement of the estimated model. And note that what this implies about our predicted values. Okay, if we look at this plot, what it implies is that we have two separate regression lines now, one for each sex of the penguin, each of the sexes, males in green and females. This is better than just one line straight through the data. It's going to be a little more accurate because now we're accounting for whether they're male or female. And we're also accounting for their flipper length. So we don't just get the same predictive value for all males, it's customized based on their flipper length. Okay. And we can see this looks like it fits the data pretty well. Like the green line captures the trend in the green points pretty well, and the blue line captures the trend in the blue points pretty well. Right. So now for this model, we could interpret those values as well. We're going to look at the case in which we have a categorical predictor with more than two groups. So in this case, the sex predictor variable only had two categories, male and female. But it gets a little more complicated. We need additional dummy variables if we have more than just two groups. So the species variable, for example, in this data set, there are Adelie penguins, or Adelie, I'm not quite sure how it's pronounced, Adelie penguins, chinstrap penguins, and gentoo penguins. If we want to use species as a predictor in modeling a penguin's body mass, we'll need two dummy variables or two indicator variables. So since species has three categories, we need two dummy variables. So in this case, just using just species as a predictor, even though it's only one categorical variable, it has two dummy variables for it. So it's actually like a two predictor model, even though the species of the penguin is our only explanatory variable. Now, what we can do is set x1 being an indicator for the penguin being a chinstrap penguin, and it's 0 otherwise. So x1 is 0 if the penguin is a gentoo penguin, and x1 is 0 if the penguin is an Adelie penguin. And then we say x2 is an indicator of the penguin being a gentoo penguin. So x2 is 0 if the penguin is a chinstrap penguin, and x2 is also 0 if it's a Adelie penguin. Adelie penguin. So based on this model, which one's the baseline or reference category? So the reference category is the one such that all the x dummy variables are 0 for it. So in this case, we have an indicator for Gentoo, we have an indicator for chinstrap. So the Adelie penguins are the baseline or reference category in this case, since this is the species for which only the dummy variables are 0. Okay. And so how would that look in a data set if we were to explicitly create these dummy variables? Well, it would look like this. So we have this indicator for species being chinstrap and another indicator for it being Gentoo. So maybe take a look at this table for a bit, pause the video if you need to, think about why these are 1s and 0s given the species column. Okay. Notice that Adelie, again, all the dummy variables are 0 because this is the baseline or reference category. And again, we don't need a third variable, species Adelie, because it would be redundant. We already know if a penguin is not chinstrap and it's not Gentoo, we know it must be Adelie because there was only 3 species in this data set. It actually causes, if you tried to incorporate a third dummy variable for Adelie, it causes issues in the numerical optimization because of the redundancy. They would actually be, the predictors would then be perfectly, we would call it collinear. It would actually be violating the multicollinearity assumption. We won't get into that in detail, but just know that we always have one less dummy variable than the number of categories in a variable in order to still fit the model using software. So now with just using species as the explanatory variable, that ends up with 2 predictors, 2 dummy variables, where we have the effect of a penguin being chinstrap, the effect of it being Gentoo, and then the reference or baseline category is taken into account via the intercept. So here's a statement of our estimated regression model where we define each term. Okay. And here we can think about how do we interpret this intercept term? Okay. Even though there's no bullet here. Let's think about the estimated intercept is 3706.2, which tells us, okay, what does the estimated intercept here tell us? Let's think about that for a moment. Let's think about y hat. Let's think about how y hat is equal to the intercept if x1 and x2 are 0. And so what does that mean? If x1 is 0, the penguin's not chinstrap. If x2 is 0, the penguin's not Gentoo. So then the penguin must be Adelie. So the estimated intercept being 3700 tells us that the expected body mass of an Adelie penguin is 3706.2 grams. So that's how we can interpret the estimated intercept for this model. We have the previous model where we have x1 being the indicator of the species of the penguin and x2 was the flipper length. Or I'm sorry, not that model. Up here. That's where it was. Yes, in this model here, x1 is the indicator of the penguin being female or male. x2 is the flipper length. Note that the flipper length being a predictor in this model now makes the estimated intercept no longer appropriate to interpret, because the intercept is the predicted value when these x's are set to being 0, which for x1, there's no problem with that, because that just means the penguin is male. But x2 is a problem, because a flipper length of 0 is outside the range of the observed data. So it would be extrapolation to interpret the intercept for this model, since a flipper length of 0 is outside the scope of the data set. Okay. Also, again, a negative predicted value in this case would not be sensible. Okay. How could we interpret this slope, though? We can talk about that. Okay, so maybe let's interpret the slope for this model real quick. We're kind of backtracking a tiny bit. But since the estimated slope for x1 since the estimated slope for x1, the indicator variable for the penguin being female, is this. To interpret this, okay, we have to be a little careful. We would say female, we expect female penguins to have a body mass that is 347.9 grams less, for the less because it's negative, less than that of male penguins holding their flipper lengths constant. So in other words, if we're comparing two penguins, one that's male and one that's female, and they each have the same flipper lengths, we would expect the female to have a body mass that's 348 grams less than that of the male. Or we could say then male penguins with the same flipper length. Now let's see how we can word this maybe a little less clunky. Since the estimate is that we expect a female penguin body mass than that of a male penguin with the same flipper length. Yeah, that's how we can word that there. So we can interpret the slope here for this model. But as I mentioned, interpreting the estimated intercept is inappropriate in this context, since a flipper length of 0 outside the scope of the observed data set. So that's how we can interpret that for that, right? And then, yeah, down here we talked about how we can interpret the estimated intercept as being the expected body mass of an Adelie penguin. And we can see that here. So 3706, if we look in this plot down here now, Adelie penguins are green. Okay. We can see right here, this line, the green line, although the blue and green lines kind of are overlapping. They're overlapping a bit. The green line is right at 3706. Okay. So that gives us the expected body mass of an Adelie penguin. We can see for Gen 2, it's a bit higher, right? So here we can interpret the other effects by saying that since the estimated slope for x1 is 26.9, okay, all the estimated slopes for dummy variables are interpreted in reference to the baseline category. Okay, so in this case, x1 is 1 for a chinstrap penguin, and the intercept corresponds to Adelie penguins. Adelie penguins are the baseline category. This tells us that on average, we expect chinstrap penguins to have body masses that are 26.9 grams higher than that of Adelie penguin. Again, it's important to include the phrasing on average or we expect. So the effect is in reference to or relative to the baseline or reference category, which is Adelie penguins. And then for x2, similarly, we can interpret this slope by saying that since the estimated slope for x2 is 1386.3, that means we expect Gen 2 the body mass is this many grams. We can see that that's the case based on the plot below, right? In the red or orangish, Gen 2 penguins are way higher. Okay, so actually this distance from the red line to the green line, this difference in heights of the two lines, is exactly what this effect is. And the 26.9 is actually the difference between the green and the blue, but it's so small on this scale, it looks like they're the same. But the Gen 2, you can see the difference in the scale. Okay. So that's how we can interpret for this model where we just have two indicator variables to use species as a predictor, we can interpret the intercept and each of the two slopes. It's all appropriate to interpret all these values here. So here's like intercept. We had interpreting the intercept, and then we had interpreting slopes for that model. All right. So now let's look at what it looks like when we model the body masses using species, which had 3 categories, along with flipper length at the same time in the model. Okay. So now we have the 2 indicator variables for species, but then we also have flipper length. So notice that the estimates for the dummy variables change dramatically when we incorporate flipper length into the model. The reason that happens is, again, due to multicollinearity, the fact that the predictors are themselves very much related to each other. So since flipper length is very much related to the species of the penguin, in other words, it's probably the case that the average flipper lengths differ significantly across the species because these are correlated or related themselves. Multicollinearity causes the coefficients to be maybe less reliable or to change significantly from a model where they're fits separate from each other. Okay, without flipper length, it changes dramatically since these are all, the predictors are correlated. So that's okay, we just have to keep that in mind as we interpret these estimates. Okay. Now in this 3 predictor model, where we're using species and flipper length as explanatory variables. X1 and X2 are our dummy variables, again for species, same as before, and X3 is the penguin's flipper length. Okay. What this implies in terms of predicted values is that within each group, within each species, Adelie, Chinstrap, and Gentoo, we have a straight line, and all of them are constrained to have exactly the same slope based on this model. The different lines here give the sets of predicted values for whether you are looking at a Gentoo penguin. Okay, so if you know the Gentoo penguin's flipper length, you can get an estimated body mass based on the straight line. And similarly for the Adelie penguins. All right. Okay. So now let's think about, for this model here, how we can interpret the estimated intercept. So since the estimated intercept is minus 40, well, instead of giving the value, we'll just say the estimated intercept is this, but since a flipper length of 0 millimeters is outside the scope or range of the observed data set, interpreting the estimated intercept is inappropriate here, since it would be extrapolation. Kind of seeing a pattern here. It's easy to fall into this trap of extrapolation being a problem, right? So 0 is way outside the scope of our data set, actually, for flipper lengths. It also just practically doesn't make sense, again, that a penguin could have no flippers. Well, I mean, sadly, I suppose it could. You could have a penguin with no flippers at all. That would be very sad. But the bigger issue is that it's outside the scope of our observed data set. So it's inappropriate to get predicted values out there. And the intercept, interpreting that, is actually a specific case of a predicted value. Specifically, it would be the predicted value. In this case, the intercept is the predicted value for a Adelie penguin with no flippers. Okay, but that's outside the scope of our data set. So if we look at Adelie, we have to look at specifically at the Adelie group too. So just within the green points, 0 is outside the range of the green points. So it's inappropriate to interpret the intercept. How do we interpret the estimated slopes here, though? Okay, so we can interpret those. So the estimated slope or regression coefficient. Estimated slope for x1 is minus 205.4. That tells us that the expected, okay, so x1 was for Chinstrap. Adelie is the baseline category. That tells us the expected body mass of a Chinstrap penguin is 205.4 grams, less than that of a Adelie penguin, I guess an Adelie penguin, holding of the same or with the same flipper length. Okay, so that's important. Now that we have flipper length in the model as a predictor as well, we need to interpret the effects conditioning on all other variables. So given all other predictors are fixed, in this case, outside of the dummy variables, the other predictor is only flipper length. So we say for a given flipper length. And then for x2, it's kind of similar. So maybe try on your own first before you see how we do it here. You could pause the video if you wanted and try. And then what we'll do, the estimated regression coefficient for x2 is 284.5. Okay. Which tells us that the expected body mass of a Gen 2 penguin, because x2 was an indicator for Gen 2 penguins, is this many grams more, since the slope or estimated coefficient was positive. We say the estimated body mass of a Gen 2 penguin is this many grams more than that of an Adelie penguin of the same flipper length. But that's how we can interpret these slopes here. And again, we can look at the plot to see that. Okay, so if we look at the same flipper length, Adelie penguins are a little bit higher. Okay, so let's say like 190. Given a flipper length of 190, Adelie penguins are a little bit higher than chin strap penguins in terms of their body mass on average. Is that what we said? Yes, we said chin strap was less than Adelie. Essentially, Adelie is greater than chin strap. Yep. And then we also said the body mass of a Gen 2 is bigger than an Adelie of the same flipper length. Okay, let's see if that's true as well. So let's look at like 210. Okay, so green right here. Yep, so the Gen 2 is higher at a given flipper length than the Adelie. So it's important that we consider it at the same flipper length, because you can see if you look at the flipper length of a typical Adelie, that's very different than the flipper length of a typical Gen 2. But note that these interpretations are happening, okay, at a fixed x value, at a fixed flipper length here. So we have to compare straight up and down across the lines. That's what we're doing here with these interpretations. Now let's look at some predicted values again. Okay, so let's use our estimated regression equation. Okay. So here, okay. So what's the expected body mass of a chin strap penguin with a flipper length of 195? So x3 is the flipper length. So we plug in 195 there. X1, okay, so we have a chin strap penguin, which means that X1 is 1. And then if it's a chin strap penguin, what is X2? It's 0, because X2 is only 1 if it's a Gen 2. Okay, so it's 0. Okay. And then let's see what Google has to say about this. And then again, important to include the units of measurement, grams. Okay. So good to show our work. We can get partial credit if we accidentally make a mistake, right? Okay, so let's again check the plot just to double check, make sure that we didn't make a bad arithmetic mistake here. Expected body mass of a chin strap penguin with 195 flipper length. Okay, let's see where that's at. So chin strap is blue, 195 is here. Okay, it looks like that's about right here. Looks like about 3,800-ish. Okay, 3,700, pretty close, right? So that seems ballpark, very reasonable. Is it extrapolation? So is a flipper length of 195 for a chin strap penguin in the range of the observed data? Yes, yeah, we have data in this area for the chin strap penguins, the blue points here. This is right in the thick of it. It's certainly valid. So it is not extrapolation to get this predicted value. So we'll say this is not extrapolation. So it's 195 is within the observed range of flipper length values for chin strap penguins. So note that it's important that it's in the range for the chin strap penguins. 220, for example, is in the range of within the range of the Gentoo penguins, but it's outside the range of the chin strap. So getting a predicted value at 220 for the chin strap would be extrapolation. It needs to be within the observed values range for that subgroup even. Okay, that's an important point. So let's say, okay, so we got that predicted value. Let's say we actually observed a penguin that was chin strap, had 195 for its flipper length, but its body mass was 3,900 grams. What is its residual? Okay, so the residual would be, okay, so in general, the residual is equal to actual value minus predicted So the observed value we were saying was 3,900. Our estimated value, or predicted value, was 3698.4. And so again, using Google, what is the calculator? So we find it at a residual of this. That many grams. Okay. So that's our residual value. The difference between the observed and the predicted value is the residual value. And what does that mean? This means that our model, what does it mean about our prediction? Was it too high, too small, or perfect? This means that our model's prediction or predicted value for this particular penguin was it too high or too low? Our predicted value was too low. Okay, because the observed response value was higher than our predicted. Our predicted undershot the prediction by a bit. That's just for one particular penguin, though. It doesn't necessarily mean our model is wrong. In general, you'll hardly ever get a predicted value that is 100% correct, right? But that's what that means there. That's how we can interpret it. Okay, and then lastly, we can think about what is the expected body mass of a chin strap penguin with a flipper length of 225 millimeters. Okay, so let's look at chin strap is in blue, 225 is out here. Uh-oh, that is well outside the observed range of values for the chin strap penguins. So it would be extrapolation to get this predicted value, which means that that predicted value is inappropriate to obtain. So since a flipper length of 225 millimeters outside the range So we don't give the predicted value. It's inappropriate due to extrapolation. The last question to think about is that when we fit this model, this constrained, okay, so we have this model with flipper length and the species dummy variables. The way this model works, it constrains the lines, although we have a separate line for each group that's vertically shifted, they have to have exactly the same slope. Just the way the numerical optimization goes for finding the estimates. Does that seem reasonable here, though? It may be the case, it could be the case that you have, like, maybe, yeah, this line fits good for the chin strap, but maybe you have something like, maybe like this line needs to be like a little steeper for the Adelie penguins, and maybe, even a little steeper yet for the Gentoo. Maybe that fits a little better where they have different slopes, right? But again, the way this model works, it forces them to be exactly forces the lines to be exactly parallel. For this data set, honestly, it looks pretty good still. Like that fits the data pretty well still, having the same exact line for slope for each group. But you may have a data set that's not the case. And if that's the case, you can allow the slope to vary within each group by incorporating what's called an interaction term between the species and flipper lengths. So we won't talk about interaction terms in this activity, but note that that would be what is needed if it looks like you need different slopes within each group, is an interaction term. For this data set, parallel slopes seems reasonable, so no interaction term is needed. All right, so that's it for this activity on dummy variables and categorical variables. Our code to do everything that we did in this activity is appended at the bottom here. And so that's it. Thanks.